In the previous video, we talked about diprotic systems or dibasic bases. We can extend the same ideas that we discussed in that video to generic polyprotic systems like triprotic acids and more. A triprotic acid, one with 3 labile protons, can dissociate 1 proton at a time according to Bronsted-Lowry. The first deprotonation event is associated with Ka1 for this acid, the second Ka2, and so on. We might also imagine the ability of the conjugate base A3- to abstract a proton from water and generate hydroxide ions in an equilibrium represented by Kb1. And we could extend that idea to all of the other intermediate. Kb1 is effectively the reverse reaction from Ka3, so we can calculate it from Kw over Ka3. Kb2 could be calculated as Kw over Ka2, and Kb3, Kw over Ka1. And furthermore, if we consider a solution with major species that include the following, we can treat them in the given ways. If a solution contains a fully protonated acid, H3A, we're going to treat this solution as though it's a monoprotic weak acid and only the first deprotonation event dominates the pH of our solution. We'll approximate the Ka of this presumed monoprotic weak acid as the Ka1 of our triprotic H3A. In a solution whose major species is H2A-, this is an intermediate form of our acid, it's amphiprotic, and as such, we can use our approximation of pH from the previous video. pH is approximately equal to pKa1 plus pKa2 divided by 2, the average of the pKa's that surround this acid's production or consumption. And therefore, similarly, if we have a solution whose major species is Ha2-, this is another intermediate form of our triprotic acid, but this time Ka's are bounded by Ka3 and Ka2. So pH can be approximated as pKa2 plus pKa3 divided by 2. The fully deprotonated form, as a major species in solution, A3-, acts like its own monobasic base. This substance, whose pH is dominated by the Kb1 for this substance. This is like a monobasic weak base with Kb given as Kb1. So we're going to apply those ideas to titrate a dibasic base. We're going to give it a generic formula B. And we're going to titrate this substance with hydrochloric acid. So this is a weak base, strong acid titration. The base has pKb values of 4 and 9 for pKb1 and 2 respectively. So we're going to sketch a titration curve for this dibasic base, which will have 2 equivalence points. One will occur after we have added 10 milliliters worth of 0.1 molar strong acid to 10 milliliters of 0.1 molar dibasic base. The second will occur after we've added 20 milliliters of hydrochloric acid. So we're going to have 2 benchmarks on our titration curve. We'll expect our pH to start high, drop rapidly, level out, go through a first equivalence point, level out, go through a second equivalence point, and then bottom out. Something that might look like this. we're going to determine the pH at 5 key points along this titration curve. Firstly, before any titrant is added right at the start of this curve. Secondly, for a point halfway in between that starting point and the first equivalence point, the pH at this first equivalence point, halfway between the first and the second equivalence points, and the pH at the second equivalence point. So, let's calculate the pH before titrant is added. To do this, consider what the major species in solution is at point number 1. Here, before we add any strong acid to our dibasic base, this substance is dominated by whichever reaction represents Kb1. This reaction here. We can approximate this, therefore, as a monobasic weak base, where Kb1 allows us to calculate the concentration of hydroxide ions at equilibrium in this reaction directly. Kb1 has a value of 1 times 10 to the negative 4, and the formal concentration of our base is 0.1 molar. So our concentration of hydroxide ions at equilibrium approximates to 3.16 times 10 to the minus 3. If we check our assumption here, alpha is 3.2%, which is okay. Our concentration of hydroxide ions, then, to a good approximation, is 3.16 times 10 to the minus 3 molar. And the pH is equal to 14 plus the log of that concentration, or 11.50. So our titration curve is going to start around 11.5. So next, let's think about what the pH is halfway to the first equivalence point at region number 2. In region number 2, we must have a buffer between our fully deprotonated base and our base which has gained 1 proton. Buffers' pHs are determined by the Henderson-Hasselbalch equation. To use the Henderson-Hasselbalch equation, this one, we need a pKa for the acidic conjugate in our buffer system. The acidic conjugate is BH+, so let's think about its Ka value. This Ka is effectively Ka2. It's the essential reverse of Kb1. So we can calculate Ka2 if we know Kw and Kb1. Therefore, our Henderson-Hasselbalch equation looks like this. pH is equal to the negative log of 1 times 10 to the minus 14 over 1 times 10 to the minus 4, plus the log of the conjugate base concentration, that is this thing's concentration, divided by the conjugate acid's concentration, this thing. How do we figure those out? Well, it turns out that we really don't need to. At the point that's halfway between our starting value and our first equivalence point, these two concentrations must be equal to each other. We have an equal number of moles of this thing reacted and this thing produced halfway between our starting value and first equivalence point. So whatever those values are, they're the same. So we'll just get the log of 1. Therefore, the pH is equal to the negative log base 10 of 1 times 10 to the minus 10, which is 10. Keeping in mind that the log of 1 is 0. So now, we have a pH 10 at this buffer region, halfway between our starting and first equivalence point values. At our first equivalence point, the major species in solution must be the first protonated substance, BH+. This is an intermediate. It's amphiprotic. It can act like an acid or like a base. When we deal with BH+ or intermediates or amphiprotic substances as major species in solution, pH is given by pKa1 plus pKa2 over 2. So we need the pKa1 and we need the pKa2 for this substance. We already showed that Ka2 for this deprotonation of BH+ is given as Kw over Kb1, or as 1 times 10 to the minus 10. Therefore, pKa2 is 10. For this fully protonated substance, BH2 plus deprotonating, we represent Ka1 as Kw over Kb2. For pKa1 value, that's equal to 5, or 14 minus 9. Thus, the pH of our intermediate form at this first equivalence point is pKa1, 5, plus pKa2, 10, divided by 2, that's 7.5. So our first equivalence point pH we expect as approximately 7.5. The pH at the point halfway in between the first and second equivalence points, point number 4 on the titration curve, is once again a buffer. This time, this buffer consists of BH+ and BH2 The concentrations of these things, like in the buffer in region 2 that we saw earlier, must be equal for the same reason as we discussed earlier. Here, though, our acidic conjugate is BH2 and our basic conjugate is the BH+. In order to calculate this buffer's pH from Henderson-Hasselbalch, we really need the pKa for this substance. Luckily, in the previous step, we've figured that out. Up here, we showed the pKa for BH2 We determined it was 5. Therefore, the pH of this buffer solution is the pKa1 for BH2 plus the log of the concentration of our conjugate base, BH+, over our conjugate acid, BH2 Because these two are the same quantities again at the halfway point between the first and second equivalence points, this becomes the log of 1 or 0. So pH is just equal to pKa1, which is 5. So at this point, our buffer in between the first and second equivalence points, we expect a pH of 5. Finally, at the second equivalence point, where we've added 20 milliliters of strong acid, we expect the major species in solution to be the fully protonated form of our base. So our major species is BH2 This substance acts like a monoprotic weak acid all by itself in solution. So BH2 undergoes deprotonation that makes H+, and BH+. This is governed by Ka1, and we've already determined that the Ka1 value for this substance is 1 times 10 to the minus 5. In order to assess this substance as a weak acid, we need to determine the formal concentration. We have diluted our original base, so it's not necessarily clear what our formal concentration is right now. Originally, we had 10 milliliters of 0.1 molar base to begin. That's 1 millimole worth of our base. We've reacted all of that base and converted it entirely into our fully protonated form, BH2 2+. So we have 1 millimole of BH2 2+ right now. Originally, we had 10 milliliters of base. So our final volume, after we've added an additional 20 milliliters of acid to the solution, is 30 milliliters. Therefore, our concentration of acid, BH2 2+, is equal to 1 millimole over 30 milliliters, 0.033 molar. Thus, Ka1, 1 times 10 to the minus 5, is equal to x squared, our equilibrium amount of H plus cation, over formal concentration 0.033 molar. This results in a solution for X, the concentration of H plus cations at equilibrium of 5.7 times 10 to the minus 4 molar. As a check, alpha is 1.7%, so we are okay here. Our pH, therefore, is the negative log of 5.7 times 10 to the minus 4, which is equal to 3.24. So we expect a pH at the second equivalence point of 3.24. And just like that, we have completed the assessment of this dibasic titration curve. So let's take a few moments to talk about identification of major species in solution so that we are confident in knowing what's present in a particular system. Firstly, in any monoprotic or monobasic system, monoprotic systems with weak acids of the form HA. In these systems, we could have HA, A-, or a combination of both. When we have both in solution, pH is given by the Henderson-Hasselbalch equation in this form. So, think about the relationship between pKa, the concentration ratio of A- and HA. When we have both of these things in solution, what dominates? Well, firstly, whenever the pH is greater than the pKa, that must mean that the log of the concentration of our base A- over our conjugate acid HA is greater than 1, meaning it's positive. Meaning that the numerator in this equation is larger than the denominator in this equation, and therefore A- is the dominant species. Similarly, when the pH of our solution is less than the pKa of our monoprotic weak acid, that must indicate to us that the log of this ratio of A- concentration to HA concentration is negative, it's less than 1. If this ratio is less than 1, or the log of this ratio is less than 1, that must mean that the numerator is smaller than the denominator, and HA dominates. We can summarize this visually if we draw out a system that looks like this, with boxes to represent major species for solutions. On one side of this box, I'll place HA. On the other side, A-. If we think about pH as increasing to the right to make basic solutions and decreasing to the left to make acidic solutions, so more acidic on the left, more basic on the right. And the dividing line between these two major species being the pKa value for our acid. Anytime the pH of a solution is less than the pKa value for our acid, the fully protonated acidic form dominates. We have enough extra H+ cations in solution, in other words, by virtue of our pH being acidic, that our fully protonated form can remain intact. But when the pH is less than the pKa for this acid, we don't have many H+ cations in solution. And so our weak acid deprotonates and forms its conjugate base, A-. In a polyprotic system, like a diprotic acid, if we think about visualizing the relationship between the pH of a solution and the major species in solution, again, we're moving to the right along this visual box, represents basic solutions. Moving to the left represents more acidic solutions. Then we can separate the distinction between H2A, the fully protonated form of our acid, and the amphiprotic form, HA-, on the basis of pKa, number 1. And the distinction between the amphiprotic form and the fully deprotonated form on the basis of pKa, number 2. So long as the pH is less than pKa 1, our fully protonated form dominates. Whenever the pH is greater than pKa number 2, our fully deprotonated form dominates. But in between those ranges, our amphiprotic form, HA- dominates. Similarly, for a triprotic system, we can generate the following visual representation. For a triprotic system, in most acidic solutions, our fully protonated form dominates up until the pH passes pKa 1 for this system, at which point the first intermediate amphiprotic form H2A- dominates, up until the point where our pH surpasses pKa 2. Then HA2-, the second intermediate amphiprotic form, dominates. At high pHs above pKa 3, the fully deprotonated form A3- dominates. In these systems, it is possible to calculate the fraction of each of the components of a monoprotic or diprotic system present. If you're interested in seeing that calculation and how it works, refer to section 10.5 in Harris. We're not going to talk about that explicitly here though, and I won't expect you to replicate that on an exam. So before we round out this chapter, let's discuss some final reflections on titrations. It's possible to carry out a titration using either potentiometric or indicator methods. Using potentiometric methods require that we have a pH electrode that constantly measures the pH of a solution as we add titrant to our analyte. This means that we must have a pH calibrated electrode. To calibrate pH, we'll use buffers of known pHs and generate a linear calibration for our probe. Analysis of a titration curve that comes from potentiometric titrations can be carried out mathematically directly. We can determine the equivalence point mathematically through the inflection of our titration curve. You remember from calculus that the determination of the inflection point for a curve is done by the second derivative test. So we need to apply a second derivative test to find the 0 point of the second derivative, or the 0 after we've taken two derivatives of our titration curve to find that inflection point. Alternatively, our goal with indicator-based titrations is to try to estimate or identify the endpoint of a reaction by a sudden change, like a change in color of a color-changing indicator. In order to accomplish this, we need to have an indicator that changes color at the equivalence point pH, whatever that might be. So, how do indicators themselves work? Indicators, or just IN for short, are substances that are themselves weak acids or weak bases with conjugate partners that are different colors in solution than our starting indicator. These are mainly large organic molecules, and as the dominant species, either the acid or its conjugate base dominate solution as a function of the pH of that solution and the pKa of that indicator, the color of the solution created by that indicator will change. For example, if we have some indicator whose completely protonated form is red and deprotonated form is blue, we can estimate where that color change from red to blue will occur. For this particular hypothetical indicator, it acts like a weak acid does in solution, and hence we only add a very small amount of it to solution to begin with. This weak acid deprotonates to form its conjugate partner. This process is determined by Ka value, which is expressed here. And when we have a mixture of the conjugates, completely protonated and deprotonated forms of this indicator in solution, the pH of that conjugate system is given by the Henderson-Hasselbalch equation. When the pH of the solution that our system exists in is greater than the pKa of the indicator, that means that the deprotonated conjugate base form of our indicator, the blue color, dominates. So we should expect our solution to be blue in that case. And similarly, if the pH of the solution that this indicator is in is less than the pKa of our indicator, that means that our fully protonated form dominates this substance, and we would expect a solution to be red in that case. So, here once again, at low pH, when pH is less than the pKa of our indicator, the fully protonated form of our indicator dominates, which is red colored. When the solution's pH is greater than the pKa of the indicator, then the deprotonated form dominates, which is blue for this indicator. For an indicator to be most effective, for us to see the most drastic and sudden color change in solution, we want our equivalence point pH to change by more than plus or minus 2 pH units from where we start our titration. So, we want to have a significant change in pH of our solution as we're titrating in order to see the most drastic color change effect in our indicator.